Hello, my name is Darren Thomas and I'm the Director of Educational Research Techniques. In this video, we're going to be taking a look at instantaneous rate of change. So let's go ahead and get started. Now, you can see up into the upper left-hand corner here that I have a line that's trying to capture what we're trying to do here when we talk about instantaneous rate of change. So what is happening is that when we had the old formula for the average rate of change, we were taking something that was slightly different from what you can see on the screen up here. And I'm going to explain that right now. So if you can look, you can see that instead of having one line, we have several lines here. And this is one of the main differences when we're talking about instantaneous versus average rate of change. What is happening is that, again, as you look at this, let me see if I can draw you a little bit of a picture to make this a little bit clearer, is that this distance, when we have just the one line, let me just draw that first. So here's my ugly graph. I know that's not how it should look. All right. And so then I have my function, if you will, kind of going like this. And then I want to try to capture the rate of change. And so I might draw, say, for example, a secant line. Let me make this a really contrasting color here. I might draw a secant line where it goes through 2 points, kind of like this. And I might draw it something like that. And so the distance from this point all the way over, this is my h value. And then going up here like this is my f of a plus h. This is what's happening. And when we're dealing with the instantaneous rate of change, what's happening is that we're making the h smaller and smaller and smaller. This is why over here in this graph to the left, we have several lines, because the first line, secant line Q1, is probably the largest h, and then you can see secant line PTQ, the kind of the blue line, is a little bit smaller. And so each time the line gets smaller and smaller, we're able to get a better and better estimate of not the average rate of change, but the instantaneous rate of change at a particular point. And so for the example here to the left, we're trying to get the instantaneous rate of change when x equals a. So when x equals a, we can tell at that particular moment what the change is. And another name for this instantaneous rate of change is the derivative, which is what we're going to be talking about now. Now, what I want to show you now is basically how we're going to adjust the formula that we use for the average rate of change to get the instantaneous rate of change. So you've seen something like this before. F of a equals f of a plus h minus f of a over h. This is all familiar, but there's something new, and there's a reason I left this gap right here. And that is because now, instead of just calculating this over 2 points, we're going to be calculating it in terms of a limit. In other words, the limit of h approaching 0 is the function of, or is the f of h plus h minus f of a over h. This is what's happening. So as we make h as small as possible, and get it smaller and smaller and smaller, we can find an idea of what the rate of change is at an exact point. So again, the theory is always hard to follow. I would rather give you an example to kind of show you what's going on here. We're going to be doing the same thing as for the average rate of change, with a slight twist that now it's a limit rather than just a simple equation. So here is our equation that we're going to be working with here. We're going to be working with the following. 3x squared plus 7x at x equals a. So this is kind of our criteria for this particular situation. And so we need to use that same equation that I just showed you, which is basically f, now it's going to be prime, f prime a, prime just means derivative, equals the limit of h approaching 0 of f of a plus h minus f of a, all this over h. That is what's happening in this particular situation. Now, this is what we do. We substitute f of a plus h, wherever we see that at, we put it in place of x. That's what's happening here. So this is what we end up getting. Let me give you a slightly different color here. So now I have 3. And so instead of x here, I'm going to have a plus h squared like that, because basically I'm just substituting wherever I see the x at, I'm going to put in the a plus h. I'm putting in a plus h every single time. That's what's happening. Plus 7a plus h. Again, that should look familiar. And that's going to equal, what is that going to equal? That's going to equal 3a squared plus 7a. So what did I do here? I took the x from over here and I put a in its place. So that's what I'm doing. I'm substituting in the different values. That's what I'm doing. So I put a plus h in over here, and it's going to equal the same thing over here, because remember, x equals a. That's kind of what's happening here. Now let's move on to our next step. And so now we're going to do some factoring. This is some basic stuff that you've already seen before. Let's see here. Let's see. Okay, so now I got f prime of a equals the limit of h approaching 0, and then we have 3 a plus h, that's this a plus h squared right here, spread out, plus 7 a plus h, that should look familiar, minus 3a squared, put that in parentheses, 3a squared plus 7a. So what I did here is I subtracted this from over here. I took it and I moved it to the left-hand side of the equation. And so now we're going to put all this over the value of h. That's what we got. Now, if we work this out, we end up kind of with the following here. So first I'm going to deal with this guy by himself. If we work this out using the FOIL method, you end up with 3a squared plus ah plus h squared, like so. And so if we simplify that out, and I need a new screen here, all right, we end up with the following. We end up with this: 3a squared plus 6ah. Now remember, let me show you what happened here. So you can see that we have these two ah's here, right here. So this is going to simplify to 2ah. And of course, we're going to multiply by 3, which is where that came from. That's why I have 6ah and also have 3a squared. So plus 3h squared plus 7a plus 7h. And now what I did right here is I'm going to remove this. I'm going to multiply everything inside here by -1. And so if I do that, I get minus 3a squared minus 7a. Just flip the signs, if you will. And of course, all this is going to be over h. We're still trying to find our rate of instantaneous change here. So now we can kind of simplify this here a little bit. So we got a positive 3a and a negative 3a. We have a positive 7a and we have a negative 7a. All that gets canceled out. And so, oh, by the way, because I'm lazy about this, this is the limit. Let's see here. This is the limit. Let me see here. All right, there we go. That's better. The limit of h approaching 0. I always forget to write that. So now we're almost done here. So the limit of h approaching 0 is after we do this simplification here. I could put that up higher. I'll put it up here. All right, there we go. 6ah plus 3h squared plus 7a, excuse me, 7a or 7h. Did I make a mistake there? Oh, wait. 7a plus 7h. Okay. Oh, the negative. Okay, I see what I did. 7a. Did I put 7a twice? Oh, I think that's what I did. I think it should only be one 7a. Okay, it should be 7. This should be 7h. Excuse me. That's a mistake right there. Plus 7h. Sorry about that. Okay, there we go. All this over h. So 6ah plus 3h plus 7a h. Okay, I see now. All right, now what we do now is we factor out the h in the top here. So if I do that, I'll get the following. I will get h, and then I will get 6a plus 3h plus 7. That's what we would get right there. And then all this is, of course, going to be over h. And of course, now we can cancel 1h. And so we're almost done. We now have 6a plus 3h plus 7. That's what we have here. And so what do we do? Remember, we can now do substitution for the limit. We can put in 0 wherever we have an h. And so if I put in a 0 here, let me just change the color. I will end up with, so put h equals 0 here. I will end up with 6a plus 3 times 0 plus 7. And that simplifies to 6a plus 7. And so that is the process for finding the instantaneous rate of change. So our rate of change in this particular example is going to be 6a plus 7. And so you can see that basically what's happening here now is that it's not so much that we're doing something new and that we have to figure out how to use tools that we already know about, how to use them to to deal with this kind of a situation. We've done factoring before, we've done substituting before, we've canceled before, we've done division before, we've done exponents before. All that is familiar. We've done limits before. But now it's like you have to figure out what tool do I use now to deal with these more complex problems, and what is the order of steps that I need to use in order to make this happen. And so we did this the long way. There's actually a very, very practical, simple shortcut for finding a simple derivative that we're going to learn in a future video. But before I wrap this video up, I just want to summarize what we talked about and move on. So in this particular video, we talked about how to find the instantaneous rate of change. In other words, instead of trying to find the average change between 2 points from a secant line over a particular function, what if we could find the rate of change at an exact point on a function? And so that involves not having maybe one value of an h, but having infinite number of values of an h. And so it becomes a limit rather than just a regular old-fashioned equation. And so when you have the limit, you keep having all these different values as you approach 0, because once you reach 0, this will become undefined, as you already probably know from other studies in math. And so by taking the limit, we can find not the rate of change over a distance, but at an exact point on the line, which can be a very valuable tool for different types of computational reasons. And so basically what we did here on this screen, although it looks ugly, was we substituted into the instantaneous rate of change, this equation over here, we substitute into it our little polynomial right here, 3x squared plus 7x. That's what we did with the criteria that x equals a. And so we put this information in there like you see on the screen, because basically what we're saying is that this guy over here equals this guy over here in many different ways. That's kind of what we said essentially. And then we substitute in appropriately. And then after doing some basic factoring in replacement or whatever you want to call it, we ended up with our final answer down here in the bottom. And so 6a plus 7, we can also replace the a with an x, because remember x equals a, and we can actually say 6x plus 7. That's kind of what's happening there. And that is the rate of change at that particular point on that particular function. So my name is Darren Thomas. I am the Director of Educational Research Techniques. Thank you for watching. Take care.